Hello everybody. In today's video, I am going to explain you how to plot transfer characteristics and output characteristics of NMOS devices in LT Spice. Right. So, what is transfer characteristics? This is all what we have done in our basic electronics course. That is, you have an NMOS, and if you vary the VGS, keeping VDS constant, you get a plot like this. This is ID versus VGS plot. So, you are plotting the current ID with respect to VGS, which is the input, and you're keeping VDS constant out here, right? So this is the curve which you get till the input gate voltage is VTH, you have negligible current. After that, it goes exponentially, it rises. You need to do this for various VDS values, not for single VDS values. So you have to do the same. You have to sweep the VGS, keeping VDS constant, but different sweeps you need to do changing the VDS value. Okay, so that is known as transfer characteristics. And similarly, what is output characteristics is the other way around, where you are sweeping VDS, keeping VGS constant, and then plotting the ID. So if you see the once VGS is 0 out here, the bottommost, even if you change VDS, there is no change in the currents. Whereas for VGS values, positive values, you will find ID is changing with respect to VGS. So this the initial portion is the linear region wherein the current changes with respect to IDS. After that, it reaches saturation where there won't be any change in the current. There won't be any significant change in the current when VDS is changing. So this the transistor is known to be in the saturation region of operation. So we need to plot these two. I am going to show you how, demonstrate to you how these two plots can be obtained in LT Spice, right? For that, first and foremost, you need to install the 180 nano TSMC 180 nanometer MOSFET model files, right? For that, if you have not done till now, then you can go to my YouTube channel, okay, and then you have a playlist known as Digital VSI. In that you have a particular video, the second video in that playlist, which is titled as TSMC 180 nanometer CMOS inverter characterization using LT Spice. Here I have explained you how to import the TSMC 180 nanometers technology library into LT Spice. So you need to do that first to proceed and try to characterize the NMOS. So first you need to do that. Okay, so you can subscribe to this channel also for the development of the channel. Alternatively, you can go to my web page. In my web page, you have a courses tab, and there you have a digital VLSI course tab. If you click that, you will get a lot of videos on digital VLSI. So the second video is again the same, in which I have explained you how to. It's the same video wherein I have explained you about CMOS inverter characterization using 180 nanometer technology. So the first part of the video is about how to import this TSMC 180 nanometer technology file. Okay, now coming to today's demonstration. So I have taken an NMOS. If I see the the width and the length, I have taken 180 nanometer as the length and width as 1 micrometer. This you need to do this SPICE directive, include TSMC 018.lib. Okay, without this won't function. So this I have explained in my earlier video. So what you need to do is you need to go to the SPICE directive, and then here type this dot include TSMC 0. So this library file which we have imported into LT Spice, so that needs to be specified so that this CMOS this NMOS will be simulated based on this directive or based on this technology library. Okay, so this is one thing which we need to do. Then see, I have taken two sources. This is VGS and VDD. Now this VDD is just the name of the source. Okay, so this VDD is the name of this source, and this is the value of the VDD. So first I am going to do the output characterization. So if you see, I have not given any DC value out here. Okay, so I have left it blank. Why is it I have kept it blank? Is I am going to use an DC sweep, right? So where do I get this DC sweeps? And if I right click, I go to simulation command. So I am doing a DC analysis now here. So if you see the DC analysis, I have taken a VDD, which is this source, that is the value of this DC value of this source. I am going to change from 0 to 1.8 volt. Okay, so these are the values which I have given where the DC for the DC analysis. Okay, so that is where this has come from 0 VDD and 1.8. So once again I am repeating this part. So DC value is to be not to be given here. Okay, the name of the component is VDD. Okay, excuse me. So that is where this has come. Now for this particular source, now I have to I am going to do a VDD sweep for various VGG values, right? So the name of the source is VN out here. Okay, the name of the source is VN, whereas the value of the for this source, okay, I have given within curly bracket VGS. Okay, that means so now the LT Spice recognizes this as a parameter which will be changed in subsequent sweeps. Okay, so that is why VGS I have given the value this as VGS for this source, the DC value within curly brackets. Now I am going to put one more spice directive. Spice directive, like I tell, you will get it from here. Spice directive. Okay, so in this I have written as dot step. Okay, that is stepwise I am going to change the value of VGS for each sweep of this DC sweep. Okay, so parameter VGS. So VGS is going to be swept from 0 to 1.8. Okay, and the step size is 0.3. Okay, so every 0.3. So first it will sweep for VGS is equal to 0. In the next sweep, DC sweep, it will be from 0. VGS will be 0.3, and then it will be 0.6, and so on and so forth. So we have defined the range 0 to 1.8 and also defined the step size. Okay, so now let me do an simulation. So I am running it. So I am going to plot the. So I am going to plot it. So this is what. So this is the desired output characteristics. You will see that this is what you for VGS is equal to 0 and VGS is equal to 1.8. So this is the VDS on the x-axis and current in the y-axis. So you have for the max current I on what we say is for VGS is equal to 1.8 and VDS is equal to 1.8. You will see it is close to 600 microampere. Okay, so this is how we get this output characteristics, right? So now if I want an transfer characteristics in which I need to sweep VGS. Okay, so what I am going to do is so I am not going to give any value to VGS. I am okay. I am removing that, and for VDD within flower bracket I am going to write VDS, right? Okay, so I am going to change this now. Okay, DC value within flower bracket VDS. Okay, so within flower bracket I have given this as VDS. So with each sweep the value will be changing out here. So DC sweep also now I am going to sweep instead of VDD I am going to this is the source name, right? V in. So I am going to sweep VD in now. Okay, so I have changed this, and here also I need to change instead of VGS now I am going to do VDS. Okay, then I am going to run this, right? So now you will find this is known as the transfer characteristics. Okay, right? So this is for the bottom green you will see for VDS is equal to 0. The VGS is swept. So and then for these are for the subsequent sweeps where VDS is increasing in the steps of 0.3 volt, and this is VGS is and this is ID. So you will find the current is exponentially increasing till VTH till the threshold voltage, which is around close to 0.5 out here for this technology 5. So till there the current is negligible. After that it is rising exponentially. Okay, so that's all for today. Thanks a lot.